Ladies and gentlemen, a very warm welcome from the Department of Electrical and Electronic Engineering and the City and Guilds College Association to the 5th Peter Lindsay Memorial Lecture. Some of you will be asking, who was Peter Lindsay? A brief answer is that he was born in Poland. He escaped from Poland in 1940. He came by a very circuitous route to Scotland, where he joined the Royal Air Force, and afterwards he received his engineering education here at City and Guilds College, after which he had an illustrious career in both academia and industry on both sides of the Atlantic. A fuller picture of Peter is painted by his colleague Alan Reddish in the brochure which you have. When he died, Peter made a very generous donation to the City and Guilds College Association to support students in need. And he also funded a memorial lecture in his name. And this is the 5th such lecture. Now to tonight's lecture. In the spring of 1921, there was a ticker tape parade in New York City. It wasn't for Charles Lindbergh or a baseball giant. It was for Albert Einstein, which is at first sight curious, because most of the people taking part in that ticker tape parade had little or probably no idea of the concepts that Einstein was proposing and discussing. But maybe not so curious, but because humans have always been fascinated by the unknown, by questions about the universe and the rules that govern it. So they wonder. We still wonder today, 90 years later. While we're going about our detailed daily business, we get excited by news of something possibly moving faster than the speed of light, or the latest on the Higgs boson. Now, such wonder implies questions that we all have about the universe and how it came about. To provide answers, two very powerful experiments are now being conducted at CERN, one of which is carried out with the compact muon solenoid. If you wonder what a compact muon solenoid is, you've come to the right place this evening. Because our speaker this evening was instrumental in designing it and is now using it to answer some of those fundamental questions about the universe. However, before I invite our speaker to give his talk, I hope you'll join with me in offering warmest congratulations to Professor Verdee on his recent election to Fellowship of the Royal Society. It's a pleasure to invite Professor Verdee to give the 5th Memorial Lecture. Thank you.
Thank you, Bob, for this very kind introduction. And also it's an honor to give this lecture in the name of Peter Lindsay. Now, one of the primary goals of physics is to understand the wonderful variety of physical phenomena that we observe around us all the time, essentially. Now, the greatest advances that have occurred in the past have been steps towards this goal. I will just mention one and give you an impression that these things are altering the way we live. So the work of Faraday and Maxwell, where they combined electricity and magnetism, and without electricity we would not be living the way we live. So that was about 130, 140 years ago. Now, what I'm going to be talking about is particle physics, we collide protons at very high energies, and these high energies existed in the early universe, a fraction of a nanosecond after the Big Bang. Now, particle physics is a modern name for centuries-old effort to understand the laws of nature, so it's not something that has come up recently. And it aims to answer two following questions. What are the elementary constituents that make up our universe? And what are the forces that control their behavior at the most basic level? Now, we can go back several thousand years and look at what the Greeks and the Indians, ancient Indians and ancient Chinese thought about this. They thought they could break everything down to four basic elements. A great philosophical leap, in fact. About 150 years ago, Mendeleev, looking at the properties, chemical properties of elements, organized them into the periodic table that we're very familiar with. We had 92 elements. About 100 years ago, Thomson, Bohr, and Rutherford actually constructed a model of the atoms with the electrons whizzing around nuclei. And so we'd gone back to two elementary elements, if you wish. So things couldn't be simpler. However, we know that that is not the full story. A lot of work that has happened in the last 100 years, some of which I'll detail. We now know that matter is composed of, for example, molecules, which are composed of atoms. Atoms have electrons going around nuclei. And probing deeper, using accelerators, we found that nuclei also have protons and neutrons. And the neutrons and protons themselves have constituents called quarks. Now, one of the questions is this the end of the story, or is there going to be further structure that we shall find? So we're probing at the LHC a size which is 100,000th the size of a proton or a neutron. So we shall see. Now, these are bound systems, so they're bound by a force. For example, the electron is bound by the electromagnetic force. So if you wanted to remove an electron from an atom, you'd have to provide energy. And that energy is about 10 electron volts. So about 10 times the battery that you see there. Now, if you wanted to remove a proton or a neutron, which is bound by the strong nuclear force, which is not the fundamental one, I'll come to that in a minute, you need something like 10 million of those. What we do at the LHC is 7 trillion of these batteries. So that's the energy that we're looking at. Now, the fundamental forces, there are 4 in nature. The strong interaction, which actually binds the quarks together. So the quarks are said to be glued together to form the neutron or proton, and these particles, for lack of imagination, are called gluons. So these are the mediator particles. So when you have a force, you have to, when you have a binding, you have to transmit some information. In fact, you transmit energy, and you transmit this energy in packets, and these packets are quanta. And the quanta of the strong interaction, the mediation, is called the gluon. For the electromagnetic interaction, it's the photon, which is familiar to us as the particle of light. And that gives us atoms. We understand light, we understand chemistry, we understand electronics. So we have quantum theories of 3 of these forces: strong, electromagnetic, weak interaction. Weak interaction is the one that is responsible for what's happening in the sun, burning of the sun. Now, the mathematics of electromagnetism and weak interaction are the same. At some very high energies, we can't tell the difference. Yet at our energies, they're wildly different. So 2 magnets repelling or attracting each other has the same equations deep down as what's happening in thermonuclear reactions in the sun. That's due to unification, the point I made right at the beginning. We don't understand how gravity actually fits into the fold yet. We don't have a quantum theory of gravity. We feel the gravitational force all the time. Now, all the known forces in the world can be attributed to these 4 interactions. Now, let me come to the work that has happened in the last 40, 50 years, stretching back to 100 years. We have had quantum mechanics and the special theory of relativity, along with the many new particles which were discovered when the accelerators came into being. And that has led us to another periodic table, which we call the Standard Model Particle Physics, and it has about 16 objects in them. On the left-hand side of this diagram, we have quarks and leptons, and they are called fermions. They're made, the matter particles are these particles. they have a quantity called spin, which as a unit of half. On the right-hand side, we have the mediators of the forces that I've just introduced. So these are packets of energy that are exchanged. For the electromagnetic, as I said, it's the photon, which is signaled by gamma, and the weak interaction by Z and W bosons, and G for the gluon. And these have twice the spin. So they spin at twice the speed as the particles on the left. We'll come to this feature in a minute. In the middle, there is a particle called the Higgs boson, which we haven't discovered, that would complete the standard model. So why is it important? So matter is composed of these fermions. There are 6 quarks and 6 leptons. There are 3 families of fermions of increasing masses. And the normal matter is made out of the first family. Now, we don't really know why there are 3 families, but there are some hints that it might have something to do with the matter-antimatter asymmetry that we observe in the universe. The interactions, I've introduced them to you, the strong nuclear, electromagnetic, and weak nuclear, are carried by the exchange of these bosons, and is a very successful description of nature at very high precision. In fact, it's a crowning achievement of 20th century science. It has been tested to thousands of times in excellent precision, yet its most basic ingredient, which is the mechanism that gives mass to the particles, is still missing. Now, what is also strange is that on the plot on the bottom right-hand side, you see a wide hierarchy of the different masses these particles that are shown on the left-hand side have. They range from the electron up to the top quark, and they vary in mass by 5 orders of magnitude. There are neutrinos there. They have a mass which we believe is non-zero, which is something like 10 to the minus 11 times the mass of the proton. So how does this hierarchy arise? We don't know. Now, one other thing that I should tell you, 2 other things I should tell you, is that when we look at stars that are rotating around the center of galaxies, especially in the spiral arms, we can measure their velocity of rotation and deduce from that what the amount of matter inside the galaxy is. Now, what we find, what the astronomers find, is that the velocity actually is much higher than would be predicted if all the mass that was inside the galaxy was due to matter that shines, the stars that shine, the stuff that we can see. In fact, that's only 1/5 of the total matter that is present. And since it doesn't shine, it has a gravitational attraction effect. We call it dark matter. Another thing that has happened recently, in the last 20 years, and the Nobel Prize for Physics was given last year for people who discovered that the rate of expansion of the universe is increasing. The expansion is accelerating. And that then has to do with something which is exerting negative pressure, or something like an anti-gravity, because gravity only pulls, it doesn't push. So that actually tells us there's a lot of other stuff in the universe which we have no clue about, but that actually dominates. That's 70% of the energy matter content of the universe. The one that I just showed you in the standard model is about 5%. There's 25% dark matter and 70% of this. So the question arises, what is dark matter? What is dark energy? And so it's a bit of an embarrassment to a certain extent. We don't know what makes 96% of our universe. I'll try to address some of these things, especially on the left-hand side one. Now, the physics of the LHC, I've broken it into 2 things which a famous Secretary of Defense actually coined, the known unknowns. So these are the things that we know we don't know, which is the origin of mass, which I will say a few words about. Why does anything have substance, in other words? And also the standard model that I showed you is incomplete. At the LHC energies, for some reactions, the answers that we get mathematically are nonsense. They go to infinity. So there's something wrong in there. It's incomplete. It's very correct, very precise at 10 times smaller energies, but at the energies of the LHC, it has some deficiencies. And there's the question, why is there no antimatter around? And I just mentioned what is the origin of dark matter. There's a symmetry that we are looking for, which is called supersymmetry, which might explain this. Now, I'll go into that, and I'll show you the results of where we stand. And the question is actually, are the matter particles, the ones that I had on the left, different from the ones on the right? We classify them as different particles, but are they really different? Another set of questions comes up. Do we live in more than 3 space dimensions. And I'll tell you something about that. Where is gravity? We don't have room for gravity inside the standard model, and perhaps the standard model will only be completed once gravity is folded in. And there are interesting theories like superstrings, and these would then lead us, the results would perhaps indicate what direction we have to take to get the ultimate unified theory that Einstein was after. And clearly we have to be prepared for the unexpected, because we are exploring unknown territory. And so when we designed our experiments, we had to bear that in mind. We have to be able to observe anything that nature is doing at this special energy scale of the LHC. Now let's look at the mass. To Newton, there are these two equations, F equals ma. So if you want to accelerate a body to a particular value of the acceleration, you have to give it a bigger force if the mass or the stuff inside it is larger. To Einstein, is E equals mc squared. We're all familiar with that equation. But he also told us that mass curves space-time, actually tells objects how to move. Now, all of this is correct, but how do objects become massive? Because without particles of mass in our bodies, we wouldn't be here talking, because we would all the particles would be traveling at the speed of light, so we would never make objects. So it goes to the heart of our existence. In fact, when we write down theories, the simplest theory actually has all the particles as massless. Very elegant, but doesn't describe nature, and that's what we want to do. So the attempt is made to say that there is a field that pervades the universe, so it's all around us. And particles interact with this field, and they acquire mass. The stronger the interaction, the larger the mass. And this field would be a quantum field, and its quantum is the Higgs boson, and finding this boson would establish the existence of the field. I keep using the word Higgs, but I should actually qualify that. There were some papers written in 1964, and there are 3 or 4 papers actually written in that year, spaced within months. And they deal with this question of the mechanism that gives mass. We call it electroweak symmetry breaking mechanism. And I've got the 2 British scientists in those 6, Peter Higgs and Tom Kibble, who's in the audience here. So in fact, we should be calling it BEHHKG boson as such. Now, so for the moment I will continue using the Higgs boson, but also one thing which is very important. Only if this theory is right shall we find the Higgs boson. We don't know the answer, otherwise we wouldn't have to do the experiments. So what do we do? So we're probing our universe, and this is the animation of an interaction, proton-proton interactions. So this is our detector CMS, and I'll describe it in a little bit more detail. There's a little hole which allows the beams to come in and out, and the 2 bunches of protons collide, and out come the particles that are produced in that collision. And these are the sort of collisions that would have been occurring, because what's happening is it's not the protons themselves, it's the quarks inside hitting head-on. And these are the types of interactions that would have been occurring a fraction of a nanosecond after the Big Bang. So we're trying to go back in time to see what existed at that time. So any particles that existed at that time, we should be able to produce in the LHC. And that's what we're trying to do. So we accelerate particles to extremely high energies, and these high energies allow us to study the young universe, because energy is also related to temperature through this relation called the Boltzmann's relation. It's E equals KT, K is a constant, Boltzmann's constant. So this allows us to go and visit times when the temperature was very high in the universe, early moments. So these are very powerful telescopes because we're looking back in time. The other thing it allows us to do is to discover new particles, because to make a particle which is very massive, you have to pump a lot of energy, and that's the Einstein's relation. And the third relation is also a very simple one. The energy is proportional to 1 over the size. So that's what happens in a microscope, and that's due to de Broglie, a French physicist last century, early part of last century. So we're actually looking deep into nature, deep inside the proton, to see what's going on. So these are very powerful microscopes as well. And we observe phenomenon particles normally no longer observable in our everyday experience. and all in a controlled way in a laboratory. So now let me just quickly tell you something about the brief history of our universe. So the Big Bang, as it took place, is conjectured that came into existence, the universe, and it's been expanding ever since. And in the initial phase, the gravitational force froze out, became distinct in its action compared to the other three. Then there was a period of very rapid expansion. We call it inflation. It's an exponential expansion. This happened at 10 to minus 35 of a second, and increased the size of the universe many, many fold. At the end of this, we don't know how it came to an end. Much of the energy density was dumped into particles which were created at that time. So these particles are like the W bosons, the Higgs bosons if it exists, and other particles like supersymmetric particles that I mentioned, also the ones that are known like the neutrinos, the muons, and gluons and quarks and so on. As the universe kept expanding, it kept cooling down, and at some point it cooled down such that the W and Z bosons, which are quite massive, could not be reproduced again, and they froze out and disappeared. And we left with a soup of quarks and gluons. And this quark, as the universe continued to expand, it continues to cool, and this quark-gluon soup coagulates into neutrons and protons and photons, for example, and neutrinos. Continues to expand, cool down. At some point, you start forming atoms and the matter that we are familiar with now. About 1 billion years after the Big Bang, the galaxies started forming. For the forming of the galaxies required some dark matter to be present. Without that, we would not have had galaxies form. We wouldn't be here talking. And then man observes what has happened. So that's a quick history. So where do we situate ourselves as far as the LHC is concerned? So when we're looking at proton-proton collisions, we're looking at this time here, which is about 10 to the minus 10 seconds or earlier. So this phase here. We also collide nuclei of lead in the LHC, and they actually create this quark-gluon soup. So we can actually create the quark-gluon soup in the laboratory and observe what happens. So I'll show you some results of that. So experimentally, it's very simple. We make the particles interact and study the products and the properties of the result of the interaction. There's one shown in the bottom there. And we measure the energy, the direction, and identity of all of the particles that come out, and reconstruct what happened using computers. So we need accelerators. We need detectors. I'll say something about that, to detect these particles. We need computing, very high requirements there for storage, CPU, and distributed analysis. And to build these instruments and the accelerator, we need collaborative science on a worldwide scale. In CMS, there are about 3,500 scientists and engineers working today. Atlas has another 3,500 from all over the world. So let me go to the accelerator. So we need to get protons. So we get protons from a gas bottle. So it's a gas of it's hydrogen gas. And so here you will see a cartoon where the protons are pulled out, the electrons stripped, and we accelerate the protons in a linear accelerator first to about 6% of the energy equivalent of the mass of a proton, then into first ring to 1.8 times, second ring about 25 times, third ring about 450 times, and finally the LHC ring 4,500 times the energy equivalent of the mass of the proton. And they're counter-rotating beams in bunches of, as I said, 100 billion protons every 50 nanoseconds today. And they collide in the heart of the experiments at 4 points. And around those points we have the detectors. And we're 100 meters underground. So the protons are accelerated by very powerful electric fields close to the speed of light, and use superconducting RF cavities, radio frequencies. So it's very much similar to what happens when a surfer picks up speed riding the water wave. Here you ride the electromagnetic waves. The protons ride the electromagnetic waves. And they're guided around the circular orbits by superconducting dipole magnets, which give them inwards kicks so they keep going around. Now the dipole magnets are a pièce de résistance, if you like, of technology. They operate at 8.3 Tesla at 1.9 degrees Kelvin, which is colder than outer space, and using superfluid helium, a liquid that was only liquefied in small quantities about 100 years ago. And we use 120 tons of this inside the LHC. It's the biggest refrigerator ever built. Protons travel in a tube which is under better vacuum, because we don't want the protons to interact with gas molecules, so we evacuate this tube to a vacuum better than outer space. Now, there are quite a few plots like this. This one is showing the stored beam energy on the vertical axis and the beam momentum on the horizontal axis. The point I wanted to make was that when we're looking at the LHC, there are many, many quantities where we push things a couple of orders of magnitude higher than what has happened before. Now, the accelerator is performing very well. This is the data that was delivered to us last year, and we measure that in terms of luminosity. We call it inverse femtobarns. It's about 5. But what it means is that we have examined 350 trillion proton-proton collisions. So the data that I'll be showing you corresponds to this number of collisions that we have examined. Now, this year, we've gone up in energy from 7 TeV to 8 TeV, and we expect to actually look at about 1,000 trillion proton-proton interactions. That's about 3 times the data that we took last year. And this is going to be necessary, as I'll point out, to establish whether the Higgs boson exists or not. And we are colliding 500 million proton-proton pairs every second when the machine is operating. So there are 4 main experiments, the general purpose, ATLAS, and CMS. They study the origin of mass and the things that I've mentioned. There's a dedicated experiment which is called LHCb, which is studying the origin of matter-antimatter asymmetry, and also has some thing to say about the first line. And a dedicated experiment called ALICE, which is looking at the general properties of this quark-gluon fluid that I mentioned. Now, the schematic of high-energy physics detector is very simple. It's like a cylindrical onion. It has 4 layers, and each of these layers has a particular function, and altogether they allow us to fulfill the mission of measuring the energies, the directions, and identity of all the particles that are produced. And they leave characteristic signatures, and these signatures allow us to tell us what the particle type is. And I'll say something about that in a few minutes. Now, if you take a slice through this cylindrical onion, that's what the CMS detector looks like. It's a huge engineering task as well. One cannot underestimate the amount of engineering effort that has gone into producing something of this nature. You can zoom in there and you'll see great detail, cables everywhere, and all laid out fairly neatly. Physicists weren't allowed to touch these things. So the first layer is the silicon tracker. It tracks the particle trajectories. It's immersed in a magnetic field. That's the solenoid. And so these bend, and the radius of curvature gives us the momentum. The second layer picks up the energies of the electrons and photons. This is made of lead tungsten crystals. The energy is deposited inside this crystal, excites the atoms of the crystal. They de-excite, emit light, and the light is picked up by photo devices. The amount of light that is picked up is proportional to the energy that has been deposited. And the third layer picks up the debris of the quarks and the gluons, and the fourth one picks up the muons, which I'll say a few words about in a minute. Now, one way to look at this is to draw an analogy with a 3D 100 megapixel digital camera. Nowadays you can get 30 megapixel digital cameras, so this one is 15,000 tons. It's 20 meters in length and 15 meters in diameter, so it's not something you can put in your pocket. It takes 40 million pictures per second, and these are pictures of what was happening a fraction of a nanosecond after the Big Bang. So it's going back in time and taking pictures of what the events of that time. And the amount of information that is produced every second is something like 10,000 encyclopedias per second. And we have to digest that information and extract it. And we then have a first selection of photographs. From 40 million, we draw it down to 100,000. And then these 100,000, with the size of a normal digital camera picture, about 1 megabyte, are then sent to a processor farm, about 20,000 processors, which are sitting on the surface, in fact, in the case of CMS. And they run computer code, which then selects 300 most interesting ones to record. And even that is a massive amount of data. So it's something like tens of petabytes per year that have to be permanently stored. So how do we detect particles in an HEP detector? So any particles that we are looking for will manifest themselves through known particles. For example, I'll talk to you about the Higgs boson into 2 photons, 2 light particles. So I'll show you this plot again, and these are the sort of particles we're looking for. So for example, this could be a picture of a Higgs boson being produced. Higgs decays into, in this particular case, if it is a Higgs boson, into 2 Z particles. One of the Z bosons, which is sitting here, decays into an electron-positron pair, which is shown here in red. And the other one goes into mu plus, mu minus, which leaves no trace in the first layer, nothing in the second, nothing in the third, and something in the fourth layer, which is shown here. So there are 2 of those. So this is how we identify. And most of the collision, for example, particles are going in the forward direction. The interesting stuff happens at 90 degrees, where the things tend to be rather clean. Now, if you wanted to look for quarks, for example, how do we observe them? So that's an interaction which I showed you earlier. Here I wanted to point out that a quark has been produced because it actually dresses itself and emerges into our detector as a collimated bunch of particles, and we call these particles jets. So they're jets of particles. You clearly see the structure here. And all we have to then do is to draw a cone around this and measure the energy that is inside this cone, and we say that is what the quark carried, or the gluon carried. Now, the neutrinos are fleeting objects. They can go right the way through the Earth and not interact, so we don't see them in the detectors, but we see infer their presence because energy momentum conservation gets violated, apparently. So this is a W going to an electron neutrino, so it's one of the particles in the, 3 of the particles in the table that I showed you earlier. You only see the electron, but nothing on the other side. So this, you know, energy momentum conservation is not violated, and neutrino has been produced. And the dark matter particle has properties very similar to the one that the neutrino has. So a quick glimpse into the construction of CMS, just to give you an idea of the timescales. So the physics drives all of the goals of the design. The physics we want, what we wanted to study as far as nature is concerned in this energy scale. So that drives the design. And in the second layer of CMS, the driving design was the Higgs boson decaying into 2 photons. I'll show you the results later on. And that meant that we had to get a device which had very high energy resolution, so we can measure the energy of the photons very precisely. And the best thing to do was to find a scintillating crystal, which detects all of the energy. And when we started, there were a few crystals around, and we have 75,000 of them. And there was a lot of R&D, prototyping, the manufacture, systems integration, installation and commissioning, and then the data taking, which we now. It took about 15 years of effort of many, many people. So then you have to put the electronics. This is what electronics at the back looks like, layers and layers of electronics. And so this, since this is an electronic and electrical engineering seminar, all of this stuff is inaccessible. And it will take us a year to access. If anything goes wrong there, then it will take us a year to get to it. So we might as well send all of this to outer space. So now the detector was assembled upstairs and lowered into the cavern 100 meters underground. So this is one of the operations. They're very spectacular operations. So what you'll see is that this object has been rolled on air-pad systems from the site here onto the center of this cover plate. This cover plate is going to open, and this device, which is 2,000 tons, is going to start lowering. It's a time-lapse photography. We started at night, at about 5 in the morning. So you can see here, this will become light. You can see the light coming down. So as the day broke, and we had to hire a special crane, which is put on the outside of this huge building. And this object has to go straight down, because the clearance on either side of the walls is just width of my hand as such. So if it's skewed a little bit, could have got stuck, and we've never had the experiment as such. So this landed at about 10 hours after the process started. And what I wanted to also point out, you can see this is quite bold. We're going to put lots of detectors inside the first 3 layers. And they will have to have cables and cooling pipes, high voltage, low voltage systems, and so all of those kind of things. 7 months later, this is what it looked like. And again, this had to have very high fidelity. Anything going wrong here would take us 3 months to access. So the experiment was closed, and it has been closed for 2.5 years, and it's all working at 99% level, so we've had no reason to actually want to open it. And once we start actually colliding, we have to select. As I mentioned, we have something like 40 million times the bunches cross, so 40 million pictures. We've got to select 300 of the best ones. And these are the ones which we want would have been occurring in the early moments of after the Big Bang. And that happens when the proton hits head-on. In fact, the quarks hit head-on, and they send a lot of energy at 90 degrees. That means the collision has been extremely violent, has a lot of energy in it, and that's the sort of collision that we would want to mimic. This particular one is producing an object called the top quark, which has a mass of 180 times the mass of the proton, higher than even the Higgs boson that we think we might be able to see. So you can see there's a lot of energy going 90 degrees. This height of these things actually is proportional to the energy. There's very little else going on. So this is that's how we select. So we select on a lot of energy at 90 degrees to the beamline. And then we send this information to the surface on 600 fibers. So it's 1 megabyte 100,000 times a second on 600 fibers to a farm up there, and the 300 are sent over there, reconstructed and in detail, and then sent out to about 10 big computer centers around the world, and then from there onwards to about 100 smaller computer centers. So within an hour or so of data being taken, they can be sitting on the laptop of somebody in China, for example, doing analysis. For this, we had to set up this worldwide computing grid. Grid is actually something that unites computing resources of the particle physics institutions around the world. And the web was invented at CERN. It allows seamless access to information that is stored in many millions of different geographical locations. The grid is infrastructure that shares the computing power and data storage capacity distributed around the globe. Now, this is a picture of what's happening. So there's about 100,000 CPUs, hundreds of petabytes of storage distributed around the world. And we have this set of people worldwide looking at the data. Now, what I wanted actually to also mention to you was we are doing this thing for the science. That's what drives us. We are very curious, and we'd like to know how the universe works. But it does have some spin-offs. Let me just give you one, which is the World Wide Web. And we are very familiar with the World Wide Web. And I've just given you something here, which reproduced a letter which was sent by the Director of Research of CERN. It says, CERN relinquishes all intellectual property rights to this code, both source and binary form, and permission is granted for anyone to use, duplicate, modify, and redistribute it. So that's the code for the World Wide Web. This was 30th of April, 1993. So it has immeasurably changed the way we do things. So it does have a very significant impact as such. And these are what I have labeled paradigm-shifting type technologies. Another one which I'll show you is pathways of innovation. So this is one of the most beautiful equations in physics. It's the Dirac's equation. I won't go through it. But I will tell you about the consequences of it. This was formulated in 1928. It's a description of electrons consistent with Einstein's special theory of relativity and quantum mechanics. And deep down had predictions. Dirac predicted the existence of antiparticles, so doubling the spectrum particles that were known at the time. So an electron would have a positron, and that is the basis of a positron emission tomography that we use. He also explained spin, and spin is the basis of magnetic resonance imaging. And the operation of the first accelerator was in 1932. And today, such accelerators are used. There are about 6,000 or 7,000 accelerators sitting in hospitals producing isotopes, which are used for medical diagnosis. There are objects like avalanche photodiodes, which we have in our experiment, which we pioneered, used in these detectors, scintillating crystals, which I mentioned, and superconducting magnets, because that's the basis of MRI scanner. So in a sense, the scientific basis of all medical imaging, functional, physiological, are steeped in nuclear and particle physics. So I don't think Dirac would have imagined that his equation would have all of these consequences. And there are many, many examples of this nature. So let me go to the science. So here's a Z boson decay into mu plus mu minus pair. So actually what we can do is to look at pairs of muons produced. I've just shown you a Z, but it can come from anything. So we actually have measured these muon pairs across a whole range of what we call mass, effective mass, in fact. So you take the energy and direction of the muons and make a quantity called the mass. It's a sort of a mass from which these two particles originate from. So we call it effective mass. So we plot it against the frequency, and that's what we see. So this was done in 2010, and you can see lots of particles here. So that's what a particle would look like. That's a Z particle. It sticks out like a sore thumb above a background. This is the upsilon particle, J psi particle. I started my PhD, this particle was not known, so the spectrum would have ended here. And in fact, half of the particles in the standard model table that I showed had not been discovered when I started my PhD. And so all of this has come since that time. Now, let me recall the physics program. So we're looking for new things. That's what the LHC was conceived for. But before we look for new things, we have to actually establish that we actually measure the things we know according to what we expect. So these signals can only be claimed after understanding the predictions of the standard model for known physics at an energy 10 times higher than the ones that we have been using previously. Now, in fact, there are a very large number of measurements we've made which indicate that the experiments are actually measuring the standard model for known physics fairly precisely. I'll give you a couple examples. So this is the same picture that I've shown you. So here what we're going to look at is to see how many times you produce a quark or a gluon at a given angle above a certain energy. So you collect the energy in a cone and you plot it at different angles and different energies, and that's the next plot. So different lines are for different angular ranges, and here is the energy, or the PT, we call it, that the quarks carried. And points are the data points, and the yellow curves are the predictions of the quantum theory of strong interactions, quantum chromodynamics. And this is about 10 orders of magnitude, and we reproduce it fairly precisely. So that's one example. Another one is to look at the mediators of the weak force, the W and Z production. So the standard model predicts how often we should produce them in these PP collisions. And this is, for example, a W. That's a Z, which I've already shown you. And these are a set of the rates, if you wish. 1 in 10 million proton-proton interactions produces a W to E nu, the one I showed you earlier. And there are very many processes which are in the process of the standard model. And the red dots are the data points, and the lines are the theory predictions. So you can see the standard model for known physics is working extremely well. So now we're ready to go and look at new stuff. So looking at the new stuff, let's start with the Higgs boson. So this plot I showed you earlier, which is a candidate for a Higgs boson, which goes into ZZ. So the Higgs actually can disintegrate into quite a few possibilities, to Zs, to photons, to B quarks, or to 2 taus, and so on and so on. So we look at all of these things, and I'll give you results on one of them. But before I do that, let me summarize the state of affairs at the end of last year, looking at the Higgs boson in wide mass range and many possibilities. If you're below this line 1, that means the Higgs boson is, standard model Higgs boson is excluded at some level, 99%. So if you did 100 experiments, 1 might see it, 99 won't see it. In this area here, which is the most interesting one, one for which, for example, the crystals were conceived in a sense, is what we are concentrating on, and that's the results I'll give you. So that's a Higgs boson going into 2 photons. You can see there's nothing in the first layer. There are cracks here, but there's nothing in the first layer, and in the second layer speaks. So these are 2 photons, and again you create this quantity called the effective mass. But before I show you the results, I'll show you some of the predictions that we were making 20 years ago. And that's what the object would look like at 4 different places. It should stick like a sore thumb. Unfortunately, this has 40 times more data than the one that I'm going to show you just now, which is this plot here. So this is the CMS plot, and that's the Atlas plot, and there's something going on here, for example, and in the case of CMS, something going on here. And that's the plot which corresponds to the one I just showed you. So this is why, to be sure that we are seeing something, we need a lot more data. So we expect to have 4 times more data, and this feature, if it is truly there, will become clearer. This is another way of projecting it, and this actually indicates that the 2 experiments are seeing something quite similar. I won't go into this plot, but an excess of events is observed, and more data are needed to ascertain the origin of this observed excess. That's the official statement. Now, a theorist has also done something where he's combined the data, because the experiments at Fermilab are also actually working. So there are 4 experiments on this plot. And you notice that there are different channels, different ways the Higgs disintegrates. And if the Higgs didn't exist, then that would be what we'd be seeing, but we're seeing something like that. Again, the error bars are very large. If you get 4 times more data, the error bars will be halved, and we get a much clearer picture. So these are tantalizing hints, and I think we are eagerly awaiting the analysis of the data we're taking at the moment. Now, even if the standard model Higgs exists, all is not completely well with the standard model alone. Of course, we will first measure the detailed properties. If you find it, that will take many, many years. And the next question is actually, and which we knew right at the beginning, why is its mass so low if it is found at this mass? Because it can float up to something like 10 to the 15 GeV by some quantum corrections. Is there a new symmetry that would protect its mass? Or if so, it should show up at the LHC. So this comes back to the question I was asking earlier. Is there a difference between matter particles and force particles? And how profound is this difference? In fact, we believe nature may indeed have put them on the same footing. Whether it's put them on the same footing at the energies that we are looking at is another issue. But this would be the ultimate symmetry in a sense, and it predicts a doubling of particles that we know, just like Dirac did 70, 80 years ago. And so for an electron, you'd have a superelectron, for example. We don't see a superelectron. It must be quite heavy. So we're looking for heavy particles. And there is circumstantial evidence that the lightest of the species actually could be the particle responsible for dark matter. So if we did see this thing, this would have profound consequences of our understanding of how the universe works. And that's a spectrum that you would expect. And this is how the event would look like in graphical form. So you produce lots of particles, lots of quarks. And these particles, which are, we label them as lighter supersymmetric particles, which would escape detection in our detectors. So let me just show you one event. That's quite an interesting event, because you can clearly see that the jets which are shown in these cones are all on one side. There's nothing on the other side. Now this can happen if a Z boson is produced against these jets and the Z decays into 2 neutrinos, so standard model actually predicts some of these things to happen. Now the question for us is, does this happen at the same rate as the standard model or a much higher rate? If it is a much higher rate, then we know something new is being produced. So we look at these things, and there's a quantity which I won't go into, and you see the data points are black. What we predict from the standard model backgrounds is shown in purple, and that's what a supersymmetry at some value would give us. Clearly, we're not seeing it yet. Now, we can incorporate gravity and see what the consequences would be, and one of the possibilities is that we live in more space dimensions than 3. And in fact, the number of dimensions actually determines the laws of physics. For example, we live in 3 dimensions, so if you take a point source and draw a sphere around it, and you put lines of force, which is what happens for electromagnetism and gravity, for example, as the radius of the sphere goes up, the surface area goes up as r squared, and the density of the lines crossing the surface area goes as 1 over r squared. So our laws of gravity and electromagnetism are 1 over r squared. If you lived in 2 dimensions, it would be a circle, and the density of lines would go as 1 over r. So you can see the laws of physics would be modified by the number of dimensions. Going to higher dimensions is a bit more difficult to visualize, but 2 is easier. So what it means is the number of space-time dimensions determines the observed form of a force. And so the gravity may propagate in higher dimensions. We don't see it because it propagates in dimensions, sizes which are too small for us to see, but we might get some evidence of that at the LHC because we're looking deep inside the protons. So this is a possibility. So it predicts particles like heavy Z bosons, we call them Z primes, at very high masses. So this is an electron-positron pair, not at 90 times the mass of the proton, but at 1,000 times. And so do we see an excess of these events or not? And that's what we see for concentrating on the right-hand side. So we get to 1,000 times the mass of the proton, and we actually see something, that's a Z there, and we don't really see anything yet. So I'll just show you something about what happens in a lead-lead collision. So this is the bunches of lead ions colliding in the CMS detector, again, similar to what I showed you. Here you can see enormous numbers of particles being produced. These are particles reconstructed by the detector, so this is a real event. So that's the power of the detector. It can actually reconstruct very large numbers of particles. And blue is the third layer singing. There are other things which is the second layer that is singing. The fourth layer doesn't really get very much. Now, what happens is that you create this fluid, which is the quark-gluon fluid, and any matter that is, any quark that is propagating through this medium will lose energy and disappear essentially. So if you were to have a collision of a quark-quark at the top of the sphere, or the surface of the sphere, one of the quarks might go out, the other one will go through the medium, and its behavior will get modified. The one that is going into free space, its behavior does not get modified. So we look for these collisions. So when you have peripheral collisions, you should see the two quarks. You should not form the quark-gluon plasma. You should see these quarks going back to back, balancing the energy. If they hit head-on, one of the quarks will dissipate. We don't violate energy momentum conservation, but we don't see the jets in the classical way. So this is what happens for a peripheral collision. For example, you can see these two spikes. Those are the two jets. And then if you get halfway head-on, that's what you see. And head-ons, the second jet has disappeared. This is a clear signature that the quark-gluon fluid has been created. There are many other signatures, and we're making quantitative measurements nowadays to understand what the properties of this fluid are. So this is the fluid that existed earlier than 1 microsecond after the Big Bang. So the outlook for the LHC. Now, I mentioned in 2012 we'll be looking at physics with 1,000 trillion proton-proton interactions. So we'll be making more precise measurements of known physics. We'll find or not whether the standard model Higgs boson exists or not. And we'll continue searching for the dark matter. The energy has gone up by 1 TeV, and it's quite significant for very heavy objects because you need a lot of energy for those. And their probabilities of production go up by 3 or 4-fold. So that's quite an interesting thing to look for. And clearly we're looking for unexpected as well, so we have to be aware of that. Now looking further ahead, the LHC will move to the design energy, so essentially doubling the energy that we are operating at the moment. So more phenomena will come within our reach, and this will happen in 2014, probably 2015. And if the Higgs has been found, then we'll be making very detailed examination of its properties to understand in which context we see it. It could be that there are more Higgs bosons than one. And so the standard model has very, very precise predictions if it is one. These predictions actually deviate if there are more. So that is the work that is still ahead of us if we were to find it. And that usually takes years of work. And then we will continue searching, it's going to new energies. And depending on the phenomena we find, then we would have to study them. And it has taken 20 years to build these detectors, and I think the physics exploitation will continue for 2 more decades. So I said I would come back to this issue of the dark side of the universe. Let me come back to that. So this is the collision of 2 clusters of galaxies. And it's a composite picture taken, reproduced by looking at images from various telescopes, Hubble, Chandra satellite, and gravitational lensing. So what you observe is the normal matter, the gaseous matter, the visible matter, interacts electromagnetically. That's how we see things. And that has actually coalesced, stopped. The dark matter, which is from gravitational lensing, we know from this picture that there's about 5 times more matter there. It has gone right the way through. Exactly the sort of properties that I was mentioning the lightest supersymmetric particle would have. It goes through our detector without detection. And it turns out that there is circumstantial evidence, as I said earlier, that we should be within reach. Now, of course, we shall find out whether this is the case. If we were to find this out, then it would have quite a big impact on our understanding. The next one I wanted to actually pick up was what happens if we do find the Higgs boson. The Higgs boson is a very peculiar particle. I've talked to you about particles which have spin half, spin 1. So there's a matter and force particles. But this is a fundamental particle which does not have spin. We've never seen something like this. So it would be quite unusual, and it has some very peculiar properties as well. In certain conditions, a collection of them exerts negative pressure. And negative pressure is something which I mentioned was responsible for things like inflation. So people ask this question, whether the dark energy is a remnant of some elementary scalar field which is analogous to the Higgs. It doesn't say that it is that. But if we were to find something like this, it actually opens up vistas in other disciplines as well, like cosmology. So it actually will give us some ideas which directions to follow. So I think these experiments are very important to do. Not doing them will essentially stop progress in physics, I believe. And so let me conclude. So the LHC project was conceived and designed to tackle some fundamental questions in science, some of which go to the heart of our existence, about the origin, the evolution, composition of our universe. So what is the origin of mass? What constitutes dark matter? Do we live in more than 3 space dimensions? And so on. These are instruments which are unprecedented in scale and complexity, and they have been driven by the science that we want to do. And we've had to push many technologies or invent technologies and push them to their limits. And the project has required long and painstaking effort on a global scale. And I think that's a tribute to human ingenuity and collaboration. Shouldn't be underestimated. The accelerators and the experiments are unparalleled scientific instruments. They're very powerful microscopes as well as very powerful telescopes. And after 20 years of design and construction, we're in the second half of this journey, that of the extraction of the science now. The accelerator and experiments are now operating very well, according to design. And the experiments have become physics-producing engines. I've concentrated a lot on the CMS detector, but there are Atlas, LHCb, and ALICE detectors, which one should not forget. We have no departures from known physics yet, but by the end of this year, we shall know if the standard model Higgs boson exists or not. We're still just at the beginning, and a long and interesting journey lies ahead, and I'll finish with this one and one more. All expectations are that what we will find at the LHC will reform our understanding of nature at the most fundamental level. And the last statement is very important. Only experiments reveal or confirm nature's inner secrets. And I would leave this for you to read and stop here. Thank you.